So today we're talking about is a dampened harmonic curve, okay, or wave, right? Because it's really a wave, right? And so it's like any spring, if we compress a spring, it's going to slowly, spring it's all the way down to equilibrium. It's going to stop springing, okay? So we've got two mass springs are experiencing dampened harmonic motion, both at 0.5 cycles per second, okay? So that means it's going to go up and back in half a second. Does that make sense? It's going to go up and back in half a second, okay? Both with initial displacements of 10 centimeters. So we start up at 10 centimeters and we let it go. So its period is going to be the 0.5, okay? Now the first spring has a dampening constant of 0.5. And so what will happen is, scientists will do tests on these and they'll figure out what the dampening constant is, okay? We can figure out the dampening constant as well. We might do that in one of these examples, okay? So let's take a look. Let's first do two pictures, okay? Let's do a picture, just a basic picture, and then we'll put it down here, okay? Just a basic picture, and then we'll graph it better here, okay? So we're going to start up at 10. So we're going to pick it up, we're going to put it up at 10, and then we're going to let go of it, okay? So we know it. 0.5 seconds, so if I go, it's going to go back to where it started. So I'm going to really briefly just kind of draw a picture, okay? So it's going to look something like this. And exact heights I don't know yet, but the calculator is going to help me get exact heights, okay? But that's kind of, and then it's going to continue, right? Continue and continue. To get the exact heights, we're going to use a calculator, okay? Now the second spring has a lesser dampening constant, so it's going to be more springy. Again, we're going to start up at 10, and we're going to, at half a second, 0.5, it's going to go through with the full cycle. Start it up, it's going down and back up. But again, this one's a little bit more springy, so I don't know exactly what it looks like, but I'm going to put it on the calculator. Let's say it looks something like this, maybe. Not much of an artist, that's for darn sure, but we got the general idea, okay? The book actually showed it and made it look much better, okay? But we're going to put it on a calculator, okay? So let's come up with an equation, okay? So the first one, using our notes, our reading, so if we look at our reading, obviously we're going to call it a cosine. Do you agree with that? We're going to call it a cosine because it starts up. So let's go y equals 10. So the equation is y equals a e to the negative ct cosine of bt, okay? That's the equation I want to use. I'm going to highlight that because that's the one I want, okay? So for our example, we're going to go y equals 10 e, now that's the number e in the calculator, right? That's the number e, to the negative, let's see, its dampening constant is 0.5, so negative 0.5, not 0.5, sorry about that, 0.5 t cosine. Now, b, remember b is equal to 2 pi divided by the curve width. Sure, thank you. Okay, so remember b, the frequency is 2 pi divided by the curve width. Well, the curve width is 0.5. And that becomes 4 pi. So it's really 2 divided by half, which makes 4, okay? Which makes 4 pi. If you don't believe me, just try it. 2 divided by 0.5 before, or if you take 2 pieces and divide them into halves, you wind up with 4 pieces, don't you? Okay. So I get my 4 pi t. Okay, there's my first equation. Second equation is going to be the same thing, right? Except for it's going to have a different dampening constant. So go y equals 10 e to the negative 0.1 t cosine. Same period, okay? So b, the frequency is going to be the same, 4 pi t. All right, there's my two equations.
What does the t stand for?
Time, great question, time. It's like within 1 second, 2 seconds. So you put the time into both places, okay? So the time, you have to put the time here because the time is going to affect the height of it. Over time, the height's going to change. So, great question. So the t goes into both. The time goes here because as time elapses, the height changes. And this changes the height. Does that make sense? And as time elapses, your cosines just continue to roll along. With smaller heights, okay?
Does it go forever?
Well, in theory, yes, but practically no, right? Does that make sense? Mathematically, we would say it goes forever, but at a certain point, you say no. Great example, okay? I'll give you an example. I got a friend who's a doctor. We were talking about half-life of medicine. So in math, you would say half-life in math goes on forever, right? Half-life, half of a half of a half of a half. But in medicine, they say 5 half-lives. That's it. So if you don't take your medicine after 5 different dosages, it gets half and half and half and half. So you go past 5. If you miss your medicine 5 times, then your medicine's going to be ineffective and you got to start all over again. So they tell patients if you miss 1 dosage, you're okay, but don't miss any more than 1 dosage. If you go for full 5 days or whatever it is, then you're in trouble, okay? So back to your question. Does it go forever? In theory, yes. In practical terms, no. That spring's going to stop, isn't it? It really is going to stop. Somebody in theory can say, well, no, I see it just barely moving. No, it stops, right? So anyway, let's graph this. So how do we graph this? It's not that hard to graph. Grab a calculator. Okay, if you need a calculator, grab one. Okay. We'll go look. I'll find one that works for me. Okay. And before we graph this, let's do a couple of really basic things. Okay. Radian mode. Okay. Why radians? Why radians? I want to ask you a really good question. Why do I need to use radian modes?
Because you're using pi?
Yes, because I'm using pi as a great example. And here's the other reason. Here's the most important reason why we use pi's. Because we want time, right? And then think about this. This is 3.14. That's why we use radians. 3.14 seconds. You roll it out, seconds, right? It's not going to be 180 degrees. Degrees are degrees, right? So we use radians because the radians match up with the arc length, okay? The arc length is the time, okay? That's why the radians is so important. So anyway, first thing, radian modes. And then the next thing I want to do is my scale. So I go to my window. And let's just match my window up to the problem, okay? So first of all, in this window, I know this is half a second, right? So maybe we would go maybe 1. Let's go, what do you think, maybe 2 seconds? You want to go 1.5? Okay, so let's go from 0 to, you want to go 1.5? I'm okay with 1.5. I'm all right with that. And then as far as my height, what's my height going to be? Yeah, so my window is going to go from probably -10 to 10. I might go a little bit higher than 10. Might go a little bit higher than 10 because right at 10 we'll see it. So I might go -10 to say maybe 15, okay? My window. And scales by maybe 0.1s. You okay with that? For the X scales, I'll go Y scales by 1s, and I'll go the X scales maybe by 0.1s. To see how the window should match up to what we want to graph, right? So we go to my window, and I was thinking I want to go 0 to 1.5. I was going to go 2, but I don't know, Elijah said 1.5, so I'm okay with that. Scales by 0.1s. Does that make sense? Because if 0.5 is 1 full cycle, we might want to see a little bit more accuracy in that. Then I wanted to go at least -10 to say 15. 10 would be right at the top, but I want to see a little bit more, a little bit higher. So I'm going to go 15, maybe 12. What do you think? Okay with 12? Mm-hmm. Yeah, okay. So then let's plug it in. Okay, Y equals, clear that. So I'm going to go at 10. Now my E to the X, so E, remember my E button? E to the -0.5 X. And you can't put T, just put X. Parentheses, cosine of 4 pi X. Okay, got it in my calculator, right? And when I push graph, it should go, ready again? Boing. You wake? Lauren? No? Okay. And let's see what happens. Graph. Boing. Hey, look at that, huh? There you go. Okay, there it is. So what's nice about this is once we have it on the calculator, we can graph it more accurately. So I know this, that if I go to my trace, I know it starts at 10. So maybe if I go 2, 4, 6, 8, 10, right? Starts up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 1 second, right? 1, 2, 3, 4, 5. There's 1.5. Actually, 1.5 worked out actually really good, Elijah.
Good job.
1.5 actually works out pretty well because it fits on my graph, doesn't it? Okay, now, here's what I can do. So, I can go ahead and do a little bit of a trace on this. So, let's go ahead and find out. So, right here, looks like I'm at a 0.75 and about a -6. But let's go ahead and roll this thing along so we get a better look at it, okay? We get a better look at it. So it goes through the x-axis at about 1.2. So about 0.1 goes through. Let's see what its min is. Its minimum is at about a 0.3, maybe 0.3 and -8. So negative 2, 4, 6, -8. So I'm down here at about -0.87. Do a little bit more tracing. You guys see what I'm doing as far as tracing to get decent. So about 0.4 I'm going through. So 0.1, 2, 3, 4 I'm going through. So I'm going to get something that looks a little bit like this, right? And then it's got to go up again. What's my other max? It's about 0.5. So 1, 2, 3, 4, 5, and it has a height of about 7.9. 1, 2, 4, 6, 7.9. There it is. See, I'm getting a pretty accurate picture if I use my trace button. All right, that's about, oh, missed it. About 0.6. So 1, 2, 3, 4, 5, 6.6. It's going to go through, and then about there, 0.75. So 0.1, 2, 3, 4, 5, 6, 7, 7.5, and about -7, almost 7. 2, 4, 6.8 is what it said. So I'm down about that. And then get my next one. I got it right about there, about maybe about 0.8, 0.9, 0.8. 1, 2, 3, 4, 5, 6, 7, 8.8. It's going to go through and about 0. Okay. And then, you know, you guys get the idea, right? And at 1, it's back up 0.6, 2, 4, 6. Okay, and you got the idea, right? Okay, now let's look at the other one. What do you expect of the other one? Tighter or looser? Okay, let's check it out. So y equals, let's put the next one in. We got a 10, and we're going to go to the e, whoops, wrong one, e to the -0.1 x cosine 4 pi x. And let's graph that one, okay? Here's the second one. Is it tighter or looser? It's looser. It's a bigger curve, right? It's looser. And it makes sense it's looser because the constant is smaller, right? So the next one, and we'll just estimate 1, 2, 3, 4. There's 10. And then we'll have our 0.1, 2, 3, 4, 5. There's 0.5, 6, 7, 8, 9, 10. There's 1. 1, 2, 3, 4, 5. There's my 0.5. So if I compare the two, the top one is the second curve. It's looser, okay? And the bottom one is the first curve. Oh, you can't see it. There you go. Okay, there's the first curve. Is the tighter one. Second curve is the top curve, which is looser. So it's just going to be the same kind of shape, except for it's just going to be a little bit looser. Okay. A little bit looser. And so forth and so on. Okay, got the idea? Now if we want to get real accurate, we just use the trace button, alright? But a general shape, there it is, okay? Not a very good art. Obviously I was not an artist. No, not at all. Okay, not hard. It's not hard. Your equation, this is your equation. Most of them are cosine because most of the time we pick a spring up and let go of it, or we pull it down. Does that make sense? But rarely would a spring start from equilibrium, right? You'd have to throw it up, which makes it a cosine, okay? All right, turn the page. All right, now, Red, Diana, and Land are still on a Ferris wheel. At t equals 0, the Ferris wheel starts turning counterclockwise. So we're going counterclockwise. So it's going that direction, right? Okay. So it's going counterclockwise. Find the equations. So one way we can do this is think of it as a curve. So we're going to actually think about where they are, and we're going to watch their height. Remember I did this yesterday? So over time, yes, they're on the Ferris wheel, they're going around and around and around. But over time, now this is a time scale, okay? So take who's at the top, okay? Take Diana, okay? Diana's at the top, right? So Diana over time is going to go like this. Right? Over time, she goes up, then she goes down, then she goes up over time, right? And the difference is that red just starts a little bit lower. Here's Diana, so red's here, right? Same start, but he would be the same things, okay? So what do we do? The easiest way to make these is to go ahead and do a little mini curve for all three of them, okay? Little mini curve for all three of them, then we'll come up with the equation, okay? So, here's red. His journey starts up here, and he's going to be like this. Right? Diana, she's going to start a little bit lower, which means her cosine curve, which where her brother is, starts back here, doesn't it? Right? Does that make sense? Landon is way back there, way behind these guys. So Landon is like way down here, okay, when it starts. Landon's down here, and his curve is going to look something like this. All right? Does that make sense? So there's Diana, there's Landon, there's red, okay? So first of all, let's come up with an equation. Probably a cosine. You guys agree with the cosine? So red, let's say red's y equals some cosine. Let's start with red, because red's the easiest. Or, I'm sorry, Diana. My bad. Oh my goodness gracious. Did I really say Diana? I'm goofing up already. Y equals, let's do Diana first. Diana's going to be some cosine. Then we'll do red and Landon, okay? So Diana starts at the top of the curve. I did Diana's wrong. Darn me. I did red. Red is behind Diana, isn't he? Red is behind Diana. Red's starting here. Yeah, so red is starting, red's in front. Diana's starting at the very highest, right? Agree, Diana's starting at the highest. And red's starting below, okay? So red's curve starts here. I know. Let me get some white out. This is why it's Friday and I do make mistakes. My bad. I'll fix it. Let's get Diana. Let's fix Diana's. Shoot. Even on film I have to admit I made a mistake. Okay, well here's Diana. Diana starts up here. And Diana goes like this. Red is ahead, right? So his journey starts here. But if we could back him up, in time, he would have been there. If we could back him up in time, he'd be here. So his curve would look like this. Okay. And Landon is way behind, right? So Landon's way behind. He's down here somewhere negative, okay? So first of all, let's get Diana's curve. Diana's curve is going to be the easiest one, and then we can do the shifts, okay? So Diana, first of all, what is the amplitude?
10.
Close, very close.
Wait.
5. It is 5. Take a look at the Ferris wheel, okay? So Diana goes up to a height of 5, equilibrium, back to 0, and then down to 5, right? She goes up to 5, back to 0, down negative 5. She goes back up to 5, 0. So you guys agree the amplitude is going to be 5, right? Does that make sense? Okay. Now, what's the period? Well, to get the period, we know it's going to be, shift over here, it's going to be 2 pi divided by the curve. Well, the curve width has got to be the time it takes to go all the way around, okay? So how much time does it take to go all the way around, okay? Yeah, so if it's 2 revolutions per minute, then it's going to be 1 revolution in 30 seconds, right? Now, do we want to do it in terms of seconds or minutes?
Probably minutes.
So if we do it in minutes, then it's 0.5. You with me? We can do it in either one. But if we do it in minutes, it's 0.5. So it's 2 pi divided by 0.5. So we're going to do it in terms of 1 revolution is 0.5 minutes, okay? We can do either one. We can do seconds or minutes, but why not just do minutes? So our frequency, B, is going to be a 4 pi, okay? So let's put a 4 pi right here. 4 pi t, okay? Now, almost done. There is no shift in Diana's curve because she started at the top, right? There's no shift in Diana because she started at the top. But there's a shift in the whole wheel. Because the wheel, I mean, the only way this thing could have no vertical shift is if the ground, let's draw the board. If the ground was right here, with me, and they dug a big hole in here so you could get into it, that's the only way that there would not be a vertical shift. But the ground is not there, the ground's right down here, okay? So, how do we find how much the curve's been brought up? What should the Ferris wheel, the center of the Ferris wheel has been moved up how many feet? 8. You guys agree with that? Yes. Plus 8. There's Diana's equation. See how that worked? Okay. Now let's go back to red. So what's the difference between red? We only have to figure out one thing. Yeah, that's all we have to do. So red's going to be the same equation. He's going to be a y equals a 5 cosine 4 pi, but parentheses t. Red's ahead, right? How much is red ahead by? How much is red ahead by? Pi force, right? So red's ahead by pi force, so we're going to go plus pi force plus 8, right? How about Landon? Everything else should be the same too. Y is equal to 5 cosine 4, well, I got to do the parentheses, 4 pi t, and then Landon got shifted how far? Well, Landon's way behind. How far behind is Landon? How far behind is Landon? 1 force, 2 force, 3 force. You guys okay with 3 force? 1 force, 2 force, 3 force. So Landon's behind 3 pi force, then plus the 8, right? Right. So he is behind, right? So he's behind. So if we put him on the curve, then he either starts, we got him starting way down here, right? Does that make sense? Because he's behind time. Great question. Okay, so now, this is such an easy question. This is such an easy question, because Will, you already answered the question. You really did. So where are all 3 riders after 30 seconds into the ride? The same spot, isn't it? Thank you, Will. Because Will said that it goes around 1 full revolution in half a second, or half a minute, right? Which is 30 seconds. So they'd be right over this. Thanks, Julia. Yeah. Does that make sense? But you gave it away, didn't you? Yeah. Okay, so homework. Now, we'll keep saying, Miss Davis, you never let us do a project. Would you like to do a project? No, see?
Yeah.
James,
No, yeah, no. See the dilemma?
It sounded like you.
Executives.
All right, well, we'll keep thinking about a project.
No, we
okay?
should. We should.
We'll keep thinking about it.
Okay.
Well, I'm doing rockets with my 4th, but rockets will be fun. All right, so for sure,
Partners for projects.
page 458, 21, 49, 57, 58, and 60. Yeah.
There is partners for projects, right?
Yeah.
Mr. Davies, you're still recording.
Huh?
You're still recording.
Oh, man, thank you.
Dylan.
Wow.
There's partners for projects.